All right, so Unit 8 deals with the area between two curves. I just want to review briefly with you. If we had a function f of x on an interval, let's say from a to b, then when we integrate from a to b f of x dx, that actually gives us the area between the function and the x-axis between these two values, a to b. So I want you to think about this for a second here. Suppose I have a graph of two functions. Let's call it, let's say this is f of x, and let's say that this is g of x. And again, we have the interval from a to b. And I want to find the area between these two functions. Not a very nice shape. It's not very regular. Can't use a rectangle. You can't use a triangle or a trapezoid or anything. I want you to think back to middle school when you were taught this problem. You were told to find the area of the shaded region. I call this the donut problem. What strategy did you use there? Hopefully you found the area of the large circle, and then you found the area of the small circle, and then you subtracted the area of the large minus the area of the small. So basically you find all of it, find the inner piece, and then you subtract it out. Well, that same idea is going to apply here. If we integrate f of x from a to b, think about what that gives us. Let me grab a highlighter here. That gives us all the area from f of x down to the x-axis. So that's all this area right there. And then let's suppose that we integrate g of x from a to b. That is, I don't know if this is going to work here, mixing highlighters here. That's all the area under g of x, between g of x and the x-axis from a to b. So then if we subtract those two things, then that's going to give you the area between the two graphs. So this gives you all of the area from f of x down to the x-axis. This gives you the area from the g of x down to the x-axis. And if we subtract out that area, you get the leftovers. So I like to write this formula. The integral from a to b of the top function minus the bottom function. Because it's not always going to be f of x and g of x, but it is always going to be top and bottom. So let's take that and let's do a problem here. I'll let you read this at your own. I'm going to explain it as we go anyway. So we want to find the area bounded by the graphs of, I lost my f here, f of x equals x plus 6, which is this line, and m of x equals x squared, which is this parabola, from x equals 0, which is the y-axis, to x equals 2. So essentially, I'm trying to find the area that I'm shading in right now. It's not a very pretty shape. It's a little bit prettier than the example I had with the wavy lines, but I need to find that area. And what I encourage my classes to do is to draw in a typical Riemann rectangle. It doesn't have to be a very big rectangle. And don't worry about the top and the bottom and should they be slanty or anything. I just want you to draw in a vertical piece, basically. And what I want to do is I want to list out all the pieces that we need to set up this integral. Okay? This helps me keep all my work organized. So my A and my B are my interval. What's the width of my interval? Well, it goes from x equals 0 to x equals 2. So A is 0 and B is 2. Now, top and bottom represent the top function and the bottom function. So visualize this rectangle. I should be able to draw it anywhere in this region. I should be able to draw it all the way over here. I should be able to draw it all the way up here to the right. I should be able to draw it anywhere. Will the top of the rectangle always touch the same function no matter where I draw it? Hopefully you're saying yes, and you realize that it is this line. Well, the top function is the line x plus 6. Same thing with the bottom function. Right? Here's the bottom of my rectangle. If I were to draw this rectangle anywhere, will it always touch the bottom function, that parabola? So I can draw my rectangle here. I can draw it up here. That bottom piece of the rectangle is always going to be touching the parabola. So my bottom function is x squared. And then we can just set up our integral. The integral from 0 to 2, bracket, the top function, x plus 6, minus the bottom function, x squared dx. And then, I know you all have calculators, because I sent them home with you, which I'm going to need them back at some point. We're going to have to figure out how to get them back. All you're going to do is you're going to type in y1, you're going to type in your top function, x plus 6. In y2, you're going to type in your bottom function, x squared. You're going to go back to your home screen and hit math 9. You're going to type in your limits, 0 to 2. And then we're going to do what? Remember, I can actually label this. This was typed in y1 and this was typed into y2. We're going to do alpha trace y1 minus alpha trace y2 dx. And we find that that is 11 and a third. So what is that? That's 34 thirds. I like improper fractions. 34 thirds. Okay, so let's do this one. Same functions, g of x equals x plus 6, r of x equals x squared. Notice what I don't have in this problem. I did not give you the interval. Up here it was 0 to 2. Down here I did not give it to you. So that's basically saying that I'm trying to find the area that's entirely between the parabola and the line. So all of this stuff. Which means I'm going to have to figure out what my interval is. So let me list this out here. A, B, top, bottom. And I'm going to draw in a typical rectangle. Doesn't matter where you draw it. I'll draw it right here. Now I want you to visualize this rectangle moving as far left as it can go. So it's going to be all the way over here in this corner. What is the x value all the way to the left? Well, it looks like it's -2. And then you're going to do the same thing. You're going to visualize it going as far right as it can possibly go. So you would have this teeny tiny little rectangle up here. Remember, these are all different size rectangles in here, just like they were with Riemann sums. This tiny little rectangle would go all the way over here to this x value, which is 1, 2, 3. So my interval in this problem is -2 to 3. My top function is still the line. X, well, I need the parentheses there. X plus 6, and my bottom function is still, x squared. Now, fortunately for me, I still have them typed into y1 and y2. So I'm going to go math 9. And everything's the same, except for instead of 0 to 2, it's going to be -2 to 3. Alpha trace y1 minus alpha trace y2 dx. And this area is, let's see if they'll change it for me, 125 over 6. That's that area. Okay, now I do want to caution you. Let me grab this piece of paper here again. Oh, that one's got writing all over it, so let's grab. These are pretty simple when you first start, but let's suppose that I give you, this guy is f of x. And let's say that this guy is g of x. And let's say we're going from A to B. And we're asked to find the area bounded by those two graphs. So that would be all of this stuff and all of this stuff. When you draw in your typical Riemann rectangle, when you draw it in here, the top function is f of x. So that would be f of x minus g of x. But if you draw it over here, your top function is g of x. So you would have to split it into two separate problems. So this one would be from A to whatever this value is, this point of intersection. Let's call it z. So the integral from A to z of top minus bottom, I'm forgetting my dx, and the integral from z to b of the top minus the bottom. It's always top minus bottom. And then you would add those two areas together. Boy, that was a hot mess. We can talk more about that later, though. What I would like for you guys to do is just try 3 and 4. Now, I did not graph them for you. If you need to use Desmos, you want to use your graphing calculator, you want to plot them by hand, whatever you want to do, but I just want you to try 3 and 4. Okay? All right, let me see how I can